It's great to be here. This is actually my first talk for a group of non-astronomers, so I'm very excited to be here and tell you a bit about what I've been working on and also technology in astronomy. So in the course of writing this talk, I realized that technology and science are intimately intertwined. So anytime you have a great advance in technology, it often leads to a great advance in scientific discovery as well. And vice versa is true. So when this happens, it results in profound changes in the world. So let's just start with a couple of examples from your life today. So everybody knows that the invention of the microscope led to the development of cell theory. Before there was a microscope, nobody could see anything small enough to know that you and I and bacteria and everything in the world is made up of cells. This led to the development of modern medicine and eventually to the effective treatment of disease. I'm willing to bet at least half of you would not be here without the invention of the microscope. So another example is semiconductors. So this originally was a discovery in physics, a device that conducts electricity sometimes, but not always. And this led to the development of the transistor in the 1950s. This moved on to be integrated circuits, modern electronics, and finally computers and the internet. This entire camp here and all the infrastructure we have would not exist without the original discovery of the semiconductor. So one person a long time ago actually realized how important technology is to science and vice versa. This is an excerpt from Alfred Nobel's will, discussing how he wants his money left. And the thing to point out here is that he said that his money should be left for the most important discoveries or inventions, or discoveries or improvements, not necessarily the most profound science. So I want to ask all of you, this is a picture of the ICMP village a few nights ago right here at camp. How many Nobel Prizes are in this picture? Anyone? Just throw some fingers up. How many you think? 5? Anyone else? 10? Okay. So in this picture, I counted that there's 7 Nobel Prizes, including the 2014 Physics Prize for the blue LED. I've seen probably hundreds of these around camp. So this kind of shows you that these kinds of discoveries, things that are awarded Nobel Prizes, actually infiltrate our entire lives, to the point where anyone sitting here at the Fab Lab cutting out a new case for the radio with the laser cutter wouldn't even think that that laser earned a Nobel Prize in 1964. So this is just something to keep in mind as we go forward. And I want to tell you a little bit about how technology has revolutionized the field of astronomy, which is where I work. So first of all, humans have been doing astronomy for thousands of years. The earliest known astronomical records are from about 8,000 years ago. So these typically took the form of drawings of phases of the moon, stars, planets, etc. But naked eye observations are really limited to where things are and how they move. One thing that technology allowed was a shift to thinking about what things are, not necessarily just where they are. So this started with the invention of the telescope in 1609. So this is a picture from Wikipedia. It's a painting of Galileo showing someone how to use a telescope. Now, at the time, this was a huge advancement. The increased magnification and resolution allowed previously impossible measurements. So, for example, the Milky Way. When people first looked at the Milky Way, they thought it was made up of some sort of nebulous gas, something glowing. But with the telescope, Galileo was actually able to resolve it into individual stars. So this was a huge deal at the time. Everyone thought it was gas and did not realize that our galaxy is made up of billions of stars. So that was something that was able to be measured in the 1600s with this simple invention of the telescope. Additionally, Galileo measured the phases of Venus. So he was able to magnify the surface of Venus enough to see that it was lit up in phases just like our moon. As Venus goes around the sun, you get starting with a crescent to half to full, and then back around the other direction. Now, at the time, this was completely revolutionary because everybody thought the Earth was the center of the universe. And of course, the church imprisoned Galileo for challenging their doctrine. But none of this would have been possible without the invention of the telescope. So I promise I'm not going to have too many equations in here, but this is kind of an important one. So when you're building a telescope, bigger is better. As telescopes get larger, you're able to resolve smaller and smaller features. The other thing is that more light will enter a bigger telescope, so that lets you see fainter objects and things that are farther away. So this is just an example from an amateur astronomy website. The question is, what can I expect to see with my telescope? And this is an image of Saturn through one of these amateur telescopes with a normal camera attached. And you can see as you get larger and larger apertures, the amount of detail and the size of the features increases as you go to larger apertures. So a big thing with telescopes was being able to increase the size of them. This is a picture of the largest optical refractive telescope ever built. So this is a telescope made with traditionally ground lenses, such as in the eyeglasses a lot of you in the audience are wearing. This is in the Yerkes Observatory, and the diameter is 0.1 meters. Now, for that diameter of telescope, the length is over 20 meters long. So this had to go in a huge building on a mount that is several times the size of me. A huge shift in the technology of telescopes was the ability to build large mirrors. So this is the largest optical telescope ever built, and the dish is 10 meters in diameter. For reference, that's probably half the size of the width of this tent, although I didn't build the tent, I don't know exactly how large it is. But the height is roughly the same as the telescope in the previous picture. You can see there's a couple people in the image at the bottom here, and in the previous picture there's some people standing there as well. And it's not an order of magnitude larger, but you've gained 2 orders of magnitude in diameter. So this was a really huge deal, being able to build bigger mirrors. The next advance in telescope technology was photography. So the original telescope observations were just done with the naked eye. You looked at what you saw, you drew in your notebook, and then the next night you would do the same thing. You could track changes this way, but it wasn't extremely precise. So photography offered 2 things. 1, longer exposure times. Your eye only sees what it sees in that instant, but you can expose a photographic plate for seconds to minutes. The next thing it offered was quantitative measurements. You could expose an image of the same star every single night and expect to get something that was relatively similar. So this allowed precise measurements of things that varied over time. So this is just an example here of what the human eye can do versus what early photographs could do. So on the right, we have Eta Carinae, which is a supernova remnant. And you can see that there's kind of some gaseous things drawn, a couple of dots, but it's kind of hard to see the structure. In the first photograph, you could actually see that there was gaseous structures and that there were many more stars than originally thought. So that photograph is from 1891. The next big advance in astronomy was modern detectors. So photographs are great, but there's a problem with them, which is that they're fundamentally analog. You take a picture, you have a physical copy, and then what do you do with it? So the data from a CCD is natively digital. Every single one of your smartphones has a CCD chip in it for the camera. And at this point, you probably don't think much about it. But at the time, it was a huge advance. And in addition to the natively digital format, they have very high quantum efficiency. And what quantum efficiency is essentially how much of the light that hits the detector is actually detected as signal. So typical photographic film, maybe 5% of the light is recorded as signal. But the highest quality CCDs at this point have up to 90% quantum efficiency. So this is one of the few plots I have in here. Oh, this laser pointer sucks, but You can see at the bottom we have what the eye is able to see. So the x-axis is the wavelength of radiation. So the eye can only see a very narrow range of visible light. The next curve up is what a traditional photograph can see. And you can see that the quantum efficiency on this log scale is around 1%, not great. And then the other curves are increasingly advanced CCDs. And you can see not only do they have much better efficiency, but they cover a much wider wavelength range. So you can see things that aren't only in the very narrow visible spectrum that the human eye can see. Finally, the last thing that's really important is that they're incredibly repeatable linear devices. If you take a picture and then take another one immediately afterwards, you should see something that is almost identical. So film in principle is a repeatable medium, but it is not nearly as repeatable as a CCD device. Okay, so every telescope observatory in the world now uses CCDs, at least the professional ones. There's a few left that still do photography for historical reasons, but scientific observatories now all use CCDs. And that was a change that occurred as late as the 1980s to 1990s. So it's really actually kind of recent. And the reason we were able to do this is because CCDs are silicon-based devices. So all of the electronics in the computers, the laptops that you're sitting here with, are fabricated on silicon wafers. And the technology to do this was actually really pushed forward by the electronics industry. So our ability to produce high-quality CCDs has benefited from this enormous progress in the microfabrication facility to build electronics. Okay, so what exactly is a CCD? It's essentially an array of MOS capacitors. So again, laser pointer's terrible, sorry. On the right, you can see a bunch of electrodes on the top. And in the top row, there's a bunch of wells where some happy electrons are sitting. They've been released from the median, and they're hanging out in this potential well because, light has hit them and freed them. How do you actually get the signal out of your detector? So the electrodes on the surface of the chip have voltage applied in a clocked pattern. And what this does is it shifts the electrons to the right off of the edge of the chip, and then they're read out in a bus on the side. So on the left of this image, I have a much more camp-like photo here. And what it is buckets full of rainwater. So it's buckets full of rainwater on a treadmill, essentially. So they go to the right, they dump their water into the buckets on the left here, and then the buckets on the left dump their water into the drain pipe on the end. And that's essentially how you read out a CCD. And the interesting thing is that not only is the detection of the electrons important, but the readout is incredibly important. You couldn't actually use these silicon-based detectors if you had no way of moving the electrons to the side and reading them out. So it's an important development that has completely changed astronomy. So this is my example of CCD versus photography. I don't know if it's easy to see on the screen. On the right, we have that same photographic plate I showed earlier from 1891. But on the left is a CCD image taken of the same region using one of the ESO telescopes. And you can see that not only do you have multicolor detection, so in a photograph you would have to use bandpass filters and take multiple images and combine them. There are multicolored CCDs, so you could just take this photo, let's say with a DSLR attached to an amateur telescope. There's many examples of this online. Or in professional observatories, they still do bandpass filters in a single color at a time and combine them. But now that it's a completely digital process, it can be done with the click of a button instead of scanning many photographs and combining them. So there's that aspect, and then also you can see that many other features in here, and that's because the CCD is sensitive out to longer wavelengths, so you can see things that are visible in the near infrared as well. I have one more example of this, and that's a galaxy cluster. So this is a slide from the 2009 Nobel Prize lecture given by Smith, and this was for the invention of the CCD. It was such an important development that a Nobel Prize was given for it. In the left image, you can see there's kind of a cluster of 4 dots. Those are some very massive galaxies. And you can see a couple other dots in there that are also galaxies, but it's not really clear that this is a galaxy cluster. In the right image, which is a CCD image, not only can you tell that these are really galaxies, but the blue arcs you see around the outside are actually gravitationally lensed galaxies that are behind the galaxy cluster. And this is something that was really only made possible with CCDs, was the ability to see these kinds of lensed galaxies. Okay, so again, I keep saying the CCD is a natively digital format, and this is important for a couple of reasons. So one, the Sloan Digital Sky Survey is a large project to map all of the galaxies within our region in the galaxy. So, in the universe, sorry. So the image on the right, the Earth is at the center of that image. And as we go outwards, the density of those dots shows you how many galaxies that this instrument has detected in that region. And this is just a small slice of their 3D data set. But what it shows you is that the universe has a clumpy structure. And this is something that is revolutionary. So the camera they use is made up of 30 CCD chips, which totals 120 megapixels. And the telescope produces 200 gigabytes of data a night. If you were doing that with photographic plates, it would literally take hundreds of years to process all of it, upload it, analyze it. But they're able to upload this and release data publicly on the internet. And if you're interested in looking at any of it, you can go to their Sky Server website and check it out. Okay, so far I've really just talked about optical astronomy. But the electromagnetic spectrum is much wider than that. So here is a plot of the atmospheric transmission. This is essentially how much light in different wavelengths gets down to Earth. On the far left, you have very short wavelengths, X-rays. As you move towards the right, the rainbow region is the visible spectrum we all know and love. Those are all the photos I just showed you. That's all of the astronomy that you probably think of when you think of what astronomers look at. But as we continue towards the right, we get to longer and longer wavelengths, and you can see that there's gaps in the atmosphere where some light does make it down to Earth, and we can observe it. And then there's a long gap where the radio waves come in. So the plot on the bottom just shows you what types of instruments are typically used for observing in those wavelengths. So X-rays, as I said, are absorbed strongly by our atmosphere, so they're only observable by satellite. We have the visible light region and the near-infrared region where there's gaps where we can observe here on Earth. There's far infrared, where again, most of the light is absorbed by the atmosphere, so we have to use satellites. And then finally, we have the radio wavelengths again, where we can observe on Earth. So I could give an entire talk on how the technology in each of these wavelengths has completely changed the field of astronomy. But since I don't have all day, I'm just going to pick one of them. Right there. So that's the red arrow is pointing to 7.35 centimeters. And there is a reason for this. So back in 1965, 2 guys, Penzias and Wilson, were working at Bell Labs. And they were able to use a very, very sensitive 20-foot horn antenna cooled to 4 degrees Kelvin. Now this, at the time, was shiny new technology. Nobody had ever played with anything like this before. And their goal was to lower the noise in their electronics and make the most sensitive measurements at 7.35 centimeters that anyone ever had in the entire world. Now, when they pointed their telescope at the sky, they found this weird buzzing. And it didn't matter what direction they pointed their telescope, it came from everywhere at the same amplitude. And these 2 guys, being the good physicists they were, said, okay, well, clearly there's something wrong with our electronics. So they spent a lot of time debugging their electronics, trying to find the source of this extra noise. And it completely eluded them. At one point, they even thought, hey, the birds have been pooping on our telescope. Maybe that's the problem. And they spent an entire day scrubbing bird poop off of their telescope. In the end, they published a paper called A Measurement of Excess Antenna Temperature at 4,080 megacycles per second in 1965. This turned out to be a really important paper, and I'll tell you why. So in the 1920s, Edwin Hubble discovered that the universe was expanding. Now, he was using one of these fancy telescopes with the big mirrors and photography plates. So at the time, advanced technology. And essentially what he found was that galaxies moved away from us faster the farther they were. And he interpreted this as the universe being smaller in the past and expanding now. So on the screen here, we just have an example. The arrow is time. On the left, you have early time. Galaxies are close together. As time moves on, they expand farther apart. Fairly simple concept. In principle, you could see it if you could look back in time. The reason this is interesting for Penzias and Wilson is because things cool off as they expand. So on the left, we have the same earlier and later time arrow, but underneath of that, we also have a temperature arrow. And as time goes on and the universe expands, it cools down. So you can see on the top, we have particles in a box, and the red wavelength would be indicative of hot photons. As it expands, we go to yellow, a little cooler. And finally, at the end, we have much farther apart particles and much cooler radiation. So an interesting thing is, if the universe is expanding, it must have been infinitely hot and dense at some point in the past. And the point where it goes from being a hot plasma, so you have free electrons and protons bouncing around, completely coupled to the radiation, to the point where the protons and electrons recombine to form hydrogen, helium, everything else in the universe, and allow the radiation to free stream, is what we call recombination. So this is a natural effect of an expanding universe. As it cools off, eventually you'll form atoms, and this radiation can now free stream through the universe. So we know this as the cosmic microwave background, and it's radiation left over from the recombination of the universe, and it has cooled as the universe expands. So at this point in our history, we would expect to see this remnant radiation sitting around in the microwave region of the spectrum. So again, universe was hotter before, now it's cooler. And these guys, for their discovery of this radiation that came from every direction in the universe at all times, were awarded the 1978 Nobel Prize in Physics for discovering this leftover radiation, which essentially gives proof of the Big Bang. If the universe was infinitely hot and dense at some point and is now expanded and cooled, it is one of the proofs that the Big Bang actually happened. So this was a Nobel Prize-winning scientific discovery that was made possible because these two gentlemen were given an incredibly sensitive horn receiver that nobody had ever used before. So I'm sure you've all seen this comic. It's from XKCD. It's been immortalized on t-shirts everywhere. And what it is it's measurements of the cosmic microwave background. So this is a black body curve, and a black body curve is defined by a specific temperature. So if you're able to measure what temperature the CMB has, you can know how old the universe is, how much it's expanded, and the time since recombination. So that's a nice comic. This is the actual data. On the plot, the blue line is a 2 Kelvin black body, the green line is a 4 Kelvin black body, and all of the dots in between are the measurements that various experiments over the years have made of the cosmic microwave background. It fits perfectly to a temperature of 2.7255 Kelvin with a very small error bar. This is the most perfect black body ever measured in the entire universe. Okay, so we're done, right? We've proved that the Big Bang happened, and this cosmic microwave background is everywhere in the universe. Unfortunately, no, we're not done. So this is a brief history of the universe. On the far left, we have what is known as the Big Bang. And essentially what this is it's a point in time where physicists say the universe is infinitely hot and dense. There were some quantum fluctuations, and then a period of rapid expansion known as inflation. So the curious thing is, if you have a completely homogeneous universe, you would never end up with stars and galaxies today. Because if everything is exactly the same, you have no way for anything to gravitationally collapse into stars or galaxies or clusters of galaxies. So there must have been something at the beginning that resulted in all of this structure we see today. So that's what we say are the quantum fluctuations at the beginning. And in principle, you should see the pattern of these fluctuations on the cosmic microwave background when you measure it. You should see small deviations from this perfect black body that we've spent so much effort measuring here. Okay, so we've already gotten this incredibly sensitive horn antenna from Bell Labs in 1965 and measured this perfect black body, and we've had many experiments afterwards to continue to do so. So how do we actually measure these incredibly small fluctuations that started as quantum fluctuations at the beginning of time? We need better detectors. So again, anytime you have an advance in science, it's usually driven by an advance in technology. The CMB is very cold. I told you in a previous slide that the temperature was 2.7 Kelvin. That means that if I'm standing in the way, you can't see the CMB behind me. I'm much too bright. So not only can you not see it, but the fluctuations are very small. We measured this incredibly perfect black body. If the fluctuations were big, the measurement would not have been so perfect. And in fact, these fluctuations are so small that they're only 1 part in 10 to the 5. Additionally, this is a super hard regime to work in. So if you remember our atmospheric transmission plot earlier, there's a lot of stuff in the atmosphere that absorbs light. And in the peak of the cosmic microwave background spectrum, you have a lot of water vapor absorption in the atmosphere. This makes it super hard to measure. So you either need to use a satellite, which is completely above the atmosphere, or you need to go to a super dry observing site on Earth. There's 2 places in the world where cosmic microwave background experiments are conducted today. One is the Atacama Desert in Chile, which is the 2nd driest desert on Earth. The other is the South Pole, which is the 1st driest desert on Earth. Additionally, you need a detector that has extremely low noise. So, okay, we can build satellites, we can go to the South Pole, but really what you need to do is you need to have the most sensitive detectors in the world to make this measurement. Okay, this is a schematic of a bolometer. It's a type of radiation detector where a small amount of energy deposited on the detector is seen as a signal. The energy you want to look at is photons, radiation. So the squiggly lines coming in from the top, those are our photons. They'll hit the detector. There's some absorber, which acts like essentially a capacitor. So I've labeled it C. You have some kind of thermometer sitting on your detector that measures how much the temperature of your absorber changes when energy hits it. And then you have a thermal link labeled G that dissipates the power to a thermal bath. And this is a really nice way to detect power. Now, the problem is, of course, if you think about this, you're measuring changes in temperature. But of course, not just light will cause the temperature to change here. Any kind of thermal changes will cause excess noise in your system. So one way to get around this is to make your bolometer cryogenic. So on the left, I have an equation for the noise equivalent power of a bolometer. And really the thing to notice there is that it's proportional to the temperature that you operate at. So the goal then is to make your detectors as cold as possible. And in fact, the temperature that we operate our detectors at in cosmic microwave background research is typically around 1/4 degree above absolute zero. So it's very cold. By the way, that is the subject of an entirely another talk. How do you actually get things that cold? But again, I don't have all day, so we'll skip over that and we can talk about it later if you're interested. Okay, so this is what a bolometer looked like in 1992. Now remember, this is a mere 30 years ago. They were handmade by a small research group at Berkeley. Essentially, graduate students sat there with tweezers and lovingly assembled these things. They're made up of nylon threads that suspend a very small membrane that has a thermistor in the middle. So this is using a germanium semiconductor thermistor. And essentially what it is it's a thermometer where when it changes temperature, the resistance changes, and you can measure that change in resistance and figure out how much power has hit your detector. Okay, so that's great, but it was not exactly background limited. It was very close, but it wasn't perfect. There was still some extra thermal noise. So the next step is to make a superconducting cryogenic detector. Again, only possible because somebody discovered superconductors many years earlier and won a Nobel Prize for that too. And essentially the idea here is you want to make your thermometer as sensitive as possible. So we've now taken our little germanium thermistor and we've replaced it with a superconducting film. And the really cool property of superconductors is that they have absolutely zero resistance until there is some very specific transition temperature. So the plot on the right shows the resistance of a superconductor as a function of temperature. And as you move higher in temperature, you suddenly have this huge jump in resistance, and then you end up with a fairly constant resistance that only changes slowly with temperature. So the idea here is that you bias your thermistor so you're sitting exactly in that very, very steep region of change in resistance with temperature. Then a very small amount of power that lands on your detector would result in a huge change in resistance. This is much easier to read out than if you have only a small change in resistance. So with the use of these superconductors as thermometers, we were able to build detectors that get to a noise floor of 50 attawatts per root hertz. For those of you who have never had to use the attawatt as a noise unit, that's 10 to the minus 18 watts. So these are incredibly low noise detectors. And still today, these are the forefront in technology for detectors in the millimeter wavelengths. Okay, so here's a picture of what these first superconducting cryogenic bolometers looked like in 1998. So you can notice we've now moved from graduate students sitting there with tweezers hand assembling these things to a graduate student trapped in the fab lab using modern silicon micromachining techniques to build these things. But there's still single chips. So you build your absorber, which is in the center of this spider web here, and then you have to hand assemble it into a focal plane at the end. So you still end up with cameras that are order tens of pixels. And the thing is, when you reach the background limit, so really the limiting noise factor is the number of photons hitting your detector, the only thing you can do is make more of them to make your camera more sensitive. So another 10 years go by, and scientists have been able to fully harness the silicon micromachining techniques used by the semiconductor industry. So essentially, we take the standard silicon wafer processing techniques used by IBM, Intel, all of these companies, and apply them to making these very sensitive detectors. I should point out that if it wasn't for the availability of this silicon micromachining technology, these detectors never would have been possible. You would have been stuck in the regime of sitting there with tweezers and nylon thread and hand assembling every detector one by one. So this kind of movement forward in technology enabled cameras of tens to move up to cameras of hundreds to thousands of pixels. So at the bottom, we just have a couple of images from, I believe these are either South Pole Telescope or APEX detectors from 2007. Okay, great. So now we have the most sensitive detectors ever built. What can we do with them? So I mentioned earlier that these quantum fluctuations at the beginning of the universe should leave an imprint on the cosmic microwave background. And in fact, by launching these detectors into space and by observing using them on the ground at the South Pole and in the Atacama Desert, we were able to uncover this fluctuation pattern in the cosmic microwave background. So moving from left to right are more and more sensitive measurements of the fluctuations, starting with the COBE mission in 1992. A Nobel Prize was awarded for that measurement as well. To the WMAP mission, which that's an image from 2003. They just completed their last data release a few years ago. And finally to the Planck data release, which was just released a few years ago in 2013. And as you can see, over time, as the detectors got better, the sensitivity got better, and we were able to see more and more detail in the cosmic microwave background. Okay, that's great. We see these bumps. What do they mean? So essentially, you can take a Fourier transform of this pattern. You have a map of the sky. You can see where it's hotter. You can see where it's dimmer. And you Fourier transform that, and what you get is a power spectrum. And you can see here there's some really nice bumps and wiggles. And the bumps and wiggles in this power spectrum are very nicely predicted by theory. So essentially, the height and spacing of these peaks can tell you things about what the universe is made of. Okay, I skipped a slide, sorry. On the right, we have omega matter, or kind of right top, that's how much matter is in the universe. And on the far left, we have the optical depth to recombination, so essentially how much stuff is between us and the time that the universe recombined. And down at the end, in kind of the damping tail of this power spectrum, you can actually measure the mass of the neutrino. At this point, we only have limits, but in principle, with precise enough measurements, you could do so. So one thing I really need to point out here is the role of big computers. It's really great that you can measure a map of the microwave sky, but you need to be able to process terabytes of data into these maps. When you scan a bolometer over a source, all you see is an increase of power for a small amount of time. You somehow have to turn that information into a map. So what you need is one, good algorithms, and two, big computers. Additionally, you need to simulate many different models of the universe to find out the one you have. And finally, you need to be able to run Markov chain Monte Carlo simulations to find the parameters of your model and fit them to the data that you have. So in order to do this, you need millions of hours of CPU time. And this is something that's really only been possible with the advent of big computing. So even if you had these amazing background limited detectors in the 1950s, you never would have gotten the results about what the universe is made of, because there's no way you would have been able to do the computations to find out. So from these super sensitive measurements, our calculations, our simulations, we've found that the universe is 4% baryons. That's what you and I are made of, the Earth, the stars, everything you can see. 26% dark matter, 70% dark energy, which we have no idea what it is, and the universe is 13.8 billion years old. So that's pretty cool. That's something that you can find out simply by measuring the fluctuations of a very uniform signal from 13.8 billion years ago. Kind of cool. Okay, so we're done, right? No, we're not done. We'll go back to our brief history of the universe for a second here. So we've looked at the fluctuations of the cosmic microwave background. So those are all those bumps and wiggles in the power spectrum. It's the hot and cold spots on the maps. But you can see that there's this period of inflation on this chart here between the quantum fluctuations and recombination. And it's a time in the history of the universe that we as physicists don't know a whole lot about, but we have a lot of theories that we would love to test. So the CMB, in addition to having fluctuations in amplitude, is also polarized. And many theories of inflation, so this period of very rapid expansion, predict that in addition to these amplitude fluctuations, you should also see some polarization. And this is left over from gravitational waves. So there's two types of polarization that you would see in the CMB. One is known as E mode, and it's what's shown on the left in this slide. So that appears, the blue spots would be cold spots in the CMB, and the red ones would be hot spots. And the E mode polarization you would see looks at either as diverging lines or as a circle going around the spot. Gravity waves produce something different called B modes, and that is a type of polarization that has a curl to it. So around hot and cold spots, you would see this kind of pinwheel pattern. And if you can measure how big the amplitude of this polarization is, you can figure out what the energy scale of inflation is. And this lets you know essentially which theories of inflation are actually viable. And you can learn something about a period of the universe. We don't know much about it right now. Okay, so this was actually the cover slide of this talk. And what this is this is a CMB polarization map from the Planck satellite. Now, the Planck satellite used these spiderweb bolometers that I showed, the ones that were made in single chips, and they put polarizers in front of them in order to make them polarized. Now, even though this satellite launched very recently, it was designed many years ago when that was state of the art. So their camera was only tens of pixels large. So this map shows mostly E modes, which are much, much brighter than the B mode polarization. So the color scheme are the hot and cold spots, which you've already seen in the temperature map. And the lines that you see, the pattern around it, are the polarization of the light. So this is really cool. We've measured polarization, but we haven't seen any of this B mode signal that we would expect from gravitational waves in the era of inflation. Okay, so again, we are just going to have to make some better detectors. So this is an image of a cryogenic bolometer array made at JPL in 2010. And what they have is a phased array of antennas, which allows them to send inherently polarized signals. So the image on the left shows the antennas, and the up and down antennas detect one polarization, and the right and left antennas detect the other. And then they have two of these nice bolometers, one for each polarization, sitting on every pixel. So they have made inherently polarization-sensitive detectors. And on top of that, they've been able to make large arrays of it. So on the right is a focal plane from this experiment that contained hundreds of pixels instead of tens of pixels. This is the map they made of the B mode polarization of the cosmic microwave background. You can see the characteristic curling pattern around the spots in the CMB. And this was a huge result that just came out last year. The thing I really like about it is this is a plot of all of the experiments that have tried to measure B mode polarization. So the colored points at the top are an array of about 10 experiments that have been trying to measure this with their cryogenic bolometer detectors, but in single pixel form, so very small numbers of detectors in their camera. And the black points are the BICEP 2 experiment with hundreds of detectors that are inherently polarized. And you can see the order of magnitude increase in sensitivity that allowed them to measure this signal. So this never would have been possible without this advance in technology. Okay, so we're done, right? No, we're still not done. So we have one more problem. And that is that the galaxy is polarized as well. It would be super awesome if you could just go out, measure the cosmic microwave background, and only see that with no contamination. But as many of you probably know, there's always contamination of some sort in any signal you're trying to measure. So this is another map from Planck, and it just shows the polarization induced by dust grains in our galaxy. So there's a magnetic field that our galaxy has, and it aligns dust grains in a preferred direction, resulting in polarization. Unfortunately, since we live in the galaxy, we have to look through this stuff and called into question the results that the BICEP team published. So the next step would be to can see multiple colors. Now, the CCD camera in your phone is inherently multicolor. That's why you get those beautiful RGB images. But until now, detectors used in millimeter wavelengths were single color. So the next advance will be to make polarization sensitive detectors that can see many colors at once. So these are photos from an experiment that's being built right now. And the cameras will be thousands to tens of thousands of pixels, and each pixel will be able to see in 3 colors. This allows you to separate components. So you can separate here, which is a higher frequency dust emission, from the lower frequency cosmic microwave background signal that you're trying to see. So again, actually, yes, we really know what happened during inflation will depend on new technology. Okay, so technology completely revolutionized the field of CMB. I really want to hit home here that without advanced detector technology, we would not know anything about the CMB other than it's an excess antenna temperature at 4 gigahertz. Another thing that's really important is signal processing and reading out many detectors. I didn't have time to talk about readout of detectors, but it's a really hard problem. And in fact, most experiments utilize tens to hundreds of FPGAs to do their onboard signal processing. And finally, the use of big computers. Personally, for my PhD thesis, I used over 1 million hours of CPU time on the NERSC supercomputer. And that was a tiny step in a much larger field. So without big computers to simulate the universe, none of this would have been possible. Okay, so now we get to the interesting part, which is the future of technology in astronomy. Everything we know about astronomy in the last 400 years is because of advances in telescopes, detectors, and computers. But while there's still many traditional hardware advances, which I really didn't have time to talk about, but would have loved to, for example, adaptive optics. We shoot giant lasers into space to correct the atmosphere. That's really cool. Modern interferometers, so combining many telescopes all over the world together to do a single measurement. Particle detectors, measuring things like neutrinos from space. There are also a bunch of new technologies that would not have been possible without computers and the internet as we know it today. So we're entering an era of big data. And many of our new challenges are going to involve computing statistics and essentially looking at just vast amounts of data. The new experiment, SKA, will be producing an exabyte of data per day. Okay, so we have these traditional advancements in technology for astronomy, but one thing that's really interesting is as we've moved to the era of the internet where we're able to openly collaborate, we've kind of broken down some of these traditional advancements and been able to look elsewhere. So one problem that we have with traditional astronomy is that every single thing you built is a custom enterprise. It's expensive, it's hard, it's time consuming, and reproducing it elsewhere is very difficult. So one thing that people are looking into is finding another way to do things. And very recently, there was a paper published called Hacking for Astronomy. Can 3D printers and open hardware enable low-cost sub-millimeter instrumentation? And this was written by a guy at the Max Planck Institute for Astronomy in Heidelberg. And what his paper focused on was, one, 3D printing custom optics for telescopes, which you can then place the designs for this on the internet, and any one of you could print your own millimeter wavelength optics. And also readout and control for your instrument. That's a very tough problem. And the development has been based entirely on the Open Hardware Association guidelines, which means that it's open for all research groups in the entire world to use and modify. Incidentally, I'd like to point out that this was inspired by the hardware hacking community. And in fact, everyone is acknowledged in the paper for inspiring this work. So thanks, everyone. You were actually a part of this. Another thing is open software. So for many years, astronomers have worked on their data analysis on their computers using their favorite code. So I use a tool called IDL. Have any of you heard of it? That's what I thought. 1, 2, maybe. But astronomers have realized that that's really not a great way to move forward. So one project that has been going on is called AstroPy, and it's a group of astronomers who are trying to build an open source Python package for all astronomical data analysis you could ever want to do. Another paper was published called Bring Out Your Codes, and essentially it was lamenting the fact that people spend all this time writing code, they publish a paper with results, but nobody ever gets to see that code and check it to make sure it's right. So a new journal has been created called the Astronomy and Computing Journal, where you can actually publish your source code and have it be not only reused by other groups, but checked to make sure that it's right. And that goes along with the astrophysics source code library. So if you're interested in that, I have the link to the paper here in the presentation. Finally, distributed computing has become a big thing. So I mentioned I used 1 million hours of supercomputer time for my thesis. That's great, but it's actually limited. There aren't that many supercomputers in the world, and it's hard to get the time. You have to propose for it, and you have to wait. So there's something called BOINC, written at UC Berkeley, and essentially it allows everyone in the world to volunteer their idle computer time for a science project that they find interesting. The most famous one that many of you probably know of is called SETI at Home. That was a screensaver that came out in the early 2000s, and it allowed the SETI project to process their radio data. Another more recent one is Cosmology at Home. I have links to both of these projects here if you're interested. The Cosmology at Home project actually uses your computer to simulate different models of the universe, so that's kind of cool. Another aspect of distributed computing is involving the public of non-experts. So many of you may be interested in simulating models of the universe on your computer, but maybe your average person would not be. So a great example of involving the broader public is something called Galaxy Zoo. I mentioned earlier that the SDSS survey creates 200 gigabytes of data a night. They've looked at millions and millions of galaxies. But if you have a poor graduate student there looking at 50 million images of galaxies, not only are they going to get bored really quick, but they'll never finish. So these guys have written a web server where volunteers can sign up and actually go through, look at images of galaxies and classify them. So not only have 50 new scientific discoveries came out of it, so that's a pretty nifty thing. Finally, there's CRAFIS, which stands for Cosmic Rays Found in Smartphones. How many of you have a smartphone in your pocket? Great. All of you could be part of a worldwide network of cosmic ray detectors. So essentially what this is every single one of your smartphones contains one of these amazing CCD chips I talked about earlier. Those CCD chips are sensitive to the light that cosmic rays create when they hit them. We have 1.5 billion smartphones on this planet. If we connected all of them to the internet, you would have the largest cosmic ray detector ever built. That's pretty cool. So if you're interested in being a part of this science project, sign up at the link below. So I hope I was able to convey to you today that hardware technology has really made a huge impact on the advancement of astronomy in many different fields in the last 400 years. But big computations have only come onto the scene relatively recently in this history of 400 years of technology. It's only really the last 20 to 30 years that this has become super important. And finally, open source hardware and software are starting to be embraced by the field. And we're hoping that this kind of new technology that's available, for example, 1.5 billion smartphones over the planet, will allow us to make new scientific discoveries that never would have been possible before. So thank you for listening to me today.
Okay, we do have about 5 minutes for some questions, so please line up at the mics to the right and then to the left if you have any questions or maybe some clarifications. Anybody? Go ahead, stage left, please.
Thank you for your talk. Very interesting. Just one question. Why did the people build this big horn antenna in 1965?
That's a very good question. I actually don't know the answer to that.
Okay, so I just wondered why they would undertake something that big and special. So was it for background? I mean, they didn't know about the background noise before, I guess.
Right. So originally it was built for another purpose, which I actually can't remember. It's on Wikipedia, so you can look it up. But actually the most interesting result was the unexpected one, which was just made possible by this technology. I think maybe the original purpose was something to do with looking at signals made on Earth by other people and other technology at the time, but I would have to look it up.
Okay, thank you.
Any more questions? We do have some more minutes left, so okay, just go ahead, stage left.
What kind of work are you doing?
Okay, so I did my PhD on the cosmic microwave background. So that is what I did for about 6 years in graduate school. Now I've switched fields to infrared astronomy. So now I'm actually more focused on shooting giant lasers into space.
For what purpose?
Okay, because we can shoot giant lasers into space. No. So the research group I work in, which is the Max Planck Institute for Extraterrestrial Physics in Garching, we're looking at two things in particular with the instrumentation I'm working on. One is we look at the galactic center. So there's a supermassive black hole at the center of our galaxy, and there's stars in orbit around this black hole. If you can very precisely measure the orbits of these stars, you can test whether general relativity is correct in the strong field limit. The other thing we look at is the formation and evolution of galaxies at high redshift, so very old galaxies. And these kinds of measurements are best done in the infrared. So I now work in a completely different wavelength range than I talked about today, and that's the near infrared.
Anybody else? We do have time for maybe one more question. Okay, go ahead.
Hello, you mentioned that rather a lot of the CCDs are silicon-based. Would there be any benefit that it isn't just of cost and the size of the detectors?
So we actually do use gallium arsenide in the infrared, which is a wavelength range I didn't talk about today. And the benefit is that you have a different band gap, so you can detect lower energy photons. So yeah, that's another entire field. It's harder because essentially the entire electronics industry is built on silicon. So all of the technology to build these detectors is readily available. When you move to more exotic things like gallium arsenide or mercury cadmium telluride, the devices, one, are much harder to build, and two, you just don't have the kind of experience and infrastructure available for silicon.
If I'm wrong, I do remember there was some sort of documentary about a race across Australia in solar-powered cars, and there was a lot of argy-bargy about one of the more corporate-sponsored ones who could just afford to plaster their vehicle with gallium arsenide photovoltaics, and everyone, it's not playing the game.